Okay, so we've been looking at things like linear equations, quadratic equations, polynomials, and so today we're going to look at a new class of functions called exponential functions. Now these are different than what we've been talking about before. We've been talking about things like x squared and x cubed and x to the fourth. And exponential functions are different. They are functions where x is in the exponent. So rather than being like x to a power, it's a base raised to the x power. So without defining a bunch of parts, I do want you to be able to identify. Okay, I made that kind of large for a reason. That's b to the x power, not b times x. Okay, and then this is what we call the base. That's why we're using the letter b. This is always a constant. This can be 2, 3, 4, 10. Okay, it can be anything that we want. And then x will be in the exponent spot. So let's look at what the general graph is going to look like, and then we're going to practice graphing one of them. So the general graph for exponential functions looks like the following. So it crosses through, go ahead and grab one of those flyers. It crosses through 0, 1. And it goes up very sharply to one direction, and then it approaches an asymptote in the other direction. And the bigger your base is, the steeper the curve is. But in general, these graphs are always going to look like this shape. So kind of like we know that all x squared graphs are going to look like parabolas. Kind of like we know that all x to the first power graphs are going to look like lines. All b to the x power graphs are going to have this shape. Okay, so it's actually significant. Notice it's going up really sharply, okay, and then it's approaching an asymptote the other direction. Okay, so there's two kind of distinct parts to that graph. So if you're asked to graph any of these types of functions, so let's just start with y equals 2 to the x. You can always set up an xy chart where you pick some x's and you plug them in and find out what their y partners are. Okay, so that's what we're going to do here. So we have I picked -2, -1, 0, 1, 2. Those are kind of my go-to points because there's a couple positives, a couple negatives. They're all small numbers. So I'm going to start with the positive ones first. Okay, so what we do is we plug these into this equation, right? So what's anything to the 0 power? So what's 2 to the 0 power? Anything to the 0 power is 1. Okay, if you don't know that, you need to jot that down. Anything at all to the 0 power is 1, which means as long as there's been no shifting, all of these types of graphs, no matter what the base is, will pass through the point 0, 1. Okay, 2 to the first power would be 2. 2 squared would be 4. But then when you get to negative exponents, we've talked about these before, but these create fractions, right? So 2 to the -2 power would be like 1 over 2 squared or 1 over 4. This would be like 1 over 2 to the first power or 1/2. Okay, so you might need to remind yourself of this, but we actually reviewed this during the very first week of class. But negative exponents give us fractions. And then let's go ahead and write down our other rule. Anything to the 0 power is 1. So let's go ahead and graph this, and we'll go out 4 in every direction because the biggest number we have represented is 4. So just like we started with the easier points when we were looking at the table, I like to start with the easier points with the graph too. So I'll start with the positive ones. 0, 1, 1, 2, 2, 4. So kind of like I said, this is the piece of the graph that goes up very, very, very sharply. Okay? It's not just going up constantly, it's going up more and more rapidly as we go. But then this other side, negative 1, up 1/2, and then negative 2, 1/4. So notice these fractions are all getting closer and closer to what? 0, right? They're never quite going to reach 0. They're always going to be 1 over something. But if you continue to make the denominator bigger, they get closer to 0. Okay, so you can use one of the lessons we did for Unit 1 in order to understand what the graphs of these various transformations of the general graph 2 to the x would be. So let's go ahead and write these down. Okay, again, that's 2 to the x power, not 2 times x. Okay, that's why I'm making it kind of ridiculously large there. This next one would be 2 to the x plus 2 power. So make sure you write that right. Negative 2 to the x power. I'm going to try to fit 3 in here, or 4 in here. And then negative 2 to the negative x power. Okay, so hopefully you remembered that lesson. Remember when I passed out that sheet of common graphs and then we had to talk about how we could change them? Well, these are new types of common graphs, but the changes remain the same. In other words, what is this plus 4 going to do to the graph of 2 to the x? It's going to raise it up 4. So I'm going to say it is like the graph in example 1, but it's shifted up 4. Okay, so I won't make you sketch that, but hopefully you can visualize what that would be, right? So you would shift this point, instead of it being at 1, it would be up at 5, and it would still have the same curve where it went rapidly up in one direction and approached an asymptote on the other direction. What about this plus 2, though? Where do you notice the plus 2 is? It's not at the end, it's where? It's like inside the exponent, right? So remember, inside plus and minuses are what kind of shifts? Left and right, and remember they work opposite in the way that you might think, right? So this is actually a left 2 shift because of the plus sign. And then what about C and D? Both of them are what kind of things? What kind of changes? When you put negative signs in various places, what happens to graphs? They reflect, right? So the one that's in front is a reflection over the x-axis. And then when it's inside, it's a reflection over the y-axis. Okay, so this is really just supposed to jog your memory. Just remember that there are actually 6 total transformations here. What's the 2 that we didn't really review just now? What are the 2 transformations that we didn't talk about in that example? Horizontal and vertical stretches and shrinks, right? So that might be something that you would see on your homework as well. In other words, all I'm doing is introducing to you a new type of function, but the transformations remain the same. So every time we learn a new function, we'll probably talk about what transformations the graph would be. All right, now, by the way, this is what 2 to the x looks like. So what would 3 to the x look like? It would look just like this, except a little bit what? Steeper, right? And 10 to the x would look just like this, but quite a bit steeper, right? So the bigger b is, what happens to the steepness? It goes up very sharply, okay? So kind of keep that in mind when we look at the next topic. So especially in this class, we are going to look at something called the exponential constant. and we use the letter E to represent that. It is not a variable. Variable implies that the value changes, and this value does not change. It's actually equal to 2.71828, 1828, and the 1828s go on forever and ever and ever. So this is a very specific type of constant that always describes exponential growth type situations. Okay. So before we talk about kind of what E represents, let's look at what the graph of e to the x would be. Okay. We're not going to do an XY table. I just want you to kind of look at your graph for 2 to the x and realize that it's still going to cross at the 0, 1. It's still going to go up sharply in this direction, and it's still going to approach an asymptote in this direction, but it's going to be slightly steeper than 2 to the x. Why do I say that? It's slightly bigger than 2, right? Like the base is slightly bigger than 2. Okay, but the general shape is the same. Now, admittedly, it'll be a little bit uglier to actually pinpoint the points, right? Because we're raising 2.71828 blah, blah, blah to powers, right? So it's going to be weird numbers you would need calculators for. Okay, and E always comes up with exponential growth. So I'm going to say E describes exponential growth situations. Some examples are population growth, the spread of disease. We've got that going on in the world right now. Okay, the spread of disease is usually not something that can be controlled. It's usually something that blows up and gets very, very large, like the graph of this is doing. Okay, as time goes on, but also money in certain investments, and we're going to learn some about that in this unit. But anything where the growth can be described as getting larger and larger and larger, quicker and quicker as time goes on, would be considered exponential growth. So E is not just a complicated number that someone made up, okay, to make you miserable, okay? It is what it is because that is literally the constant that always comes up with these types of growth situations. Much like pi always comes up when you measure what kind of shape? Circles, right? Nobody came up with pi. Pi is the ratio that occurs when you try to measure a circle, okay? And E is the ratio that comes up when we try to measure exponential growth, things like population, disease, spreading, money, so on and so forth. Okay, so we're going to take a pause here and we're going to review our laws of exponents. We reviewed these on the first week, but I kind of told you I'm kind of a review as we go kind of teacher, so I want to make sure that we really, really know the laws of exponents because frankly later on in the week we're going to be talking about the cousin to exponential functions called logarithms, and so the better you understand exponents, the easier logarithms is to understand as well. Okay, so back in the first week, we talked about 3 main rules, and then we're going to kind of jump off of those. So the first one is the product rule, and here's what the product rule says in notation form. If you have b to the x times b to the y, it is the same as b to the x plus y. Okay, so the rule says that as long as the bases are the same, when multiplying terms with exponents, just add the exponents. So it is important to note that the bases have to be the same. If the bases aren't the same, you actually can't combine them at all. Okay, so let's look at a few examples just to make sure if we remember the rules or not. And I feel like some of these are a little easier to apply the rules. So let's start easy first. If I asked you to simplify x to the 5th times x squared, what would you do with those exponents? Notice the bases are the same, right? The base is x in both cases. So then you would do what with those exponents? Add them, so this would be x to the 5 plus 2 power, or x to the 7th. Okay, so notice we didn't do anything with the base. We just kept it the same. Okay, so sorry my pen is kind of light here. I forgot all my markers that write a little darker. But make sure you know how to apply it when the base is a number as well. In other words, I almost always have students who really want to multiply that 3 times 3. But we're not supposed to multiply until we've taken care of what first? Exponents come first, right? So just like the one above it, you don't do anything with the 3 and you just do what with the exponents? You add them. So this would be 3 to the 15th. Okay, you would not multiply 3 times 3. Think of like 3 to the 6th and 3 to the 9th as partners. You can't separate them. It's not just 3, it's 3 raised to the 6th power, so I have to treat it like an exponent because that's what it is. But what about when we have maybe the same bases, but the exponents are unusual, like the exponential functions we're going to be looking at. Notice these are exponential functions because the x is located where? What's different about the third example from the previous two? X is actually in the exponent location, right? So it's like a number base raised to a power. So, but the exponent rule still applies. It would be 10 to the x plus 4x power, and then you could combine those to be what? 10 to the 5x. Okay, so that's the first rule of exponents. The second rule of exponents is the quotient rule. So the quotient rule just says if you have b to the x over b to the y, it's the same as b to the x minus y power. So here's the rule kind of explained out in words, as long as the bases are the same, because again, if they're not, you can't do simplification. They're not considered like terms if the bases aren't the same. So as long as the bases are the same, when dividing terms with exponents, subtract the exponents. All right, so let's do some kind of varied examples for this rule too. Again, I don't just want to start with easy ones and then that's all we do. So notice we have the same base, right? We are dividing terms with exponents. It's x to the 10th divided by x to the 13th. So what are we supposed to do with those exponents? Subtract them and the base stays the same, right? So we end up getting x to the negative third, which I do want you to know rewrites into 1 over x to the third. Okay, so remember we wrote this down before, but negative exponents give us fractions. So we actually move it to the other part of the fraction. So if you have something to a negative power, it's 1 over that thing to the positive power. What about this one? X to the 5th over x to the negative third. So same rule, right? Bases are the same, for sure. So what do I need to do with the exponents? Subtract them. So just be careful about signs, right? It'll be x to the 5 minus negative third power, but then that's going to change to plus, right? So we're just going to get x to the what? 8th. Okay, so it's top exponent minus bottom exponent. In this case, we had a double negative because the bottom exponent was negative. So what about when you have a little more unusual exponents like this? So for the same reason we don't multiply the 3's in our previous example with product rule, you're not going to cancel out the negative 3's really here either. Okay? Notice the bases are the same. So what happens to the base when the bases are the same? Nothing, right? We only really work with the exponents, right? We leave the base the same. Okay? And then we would say to the 5 minus 3 power, which is the same as negative 3 squared, which we could figure out, right? What is negative 3 times itself? Positive 9, right? Okay. Note that since I wanted to raise negative 3 to a power, I put that negative 3 in parentheses. So when you're using your calculator, when you're trying to write it out, make sure that you use parentheses when necessary. All right, so let's do one with some variables too, just to make sure we remember the rule. So what about 10x divided by 10 to the 8x power? So it's definitely quotient rule, right, because we're dividing. The bases are the same, so the base isn't going to change. And what do I need to do with the exponents in general? Subtract them, so it's going to be x, take away 8x, which is going to be 10 to the negative 7x power. Okay. Generally, I don't want you to leave a question with a negative exponent, or an answer, rather, with a negative exponent. So how could I rewrite this so that it would have a positive exponent? 1 over 10 to the 7x power. Okay, so just like we don't leave 2/4 as our answer, we reduce it to 1/2. I want you to reduce negative exponent answers to positive fractions. Okay, so fractions with positive exponents. All right, so there is product rule, quotient rule, and then the third rule is power rule. So this is for when you have an exponent being raised to a second power. And when that happens, you are supposed to do what with the exponents? If you remember from the first week? Multiply them? Okay. So here's the explanation of that rule. When raising an exponential term to another power, multiply the exponents. Notice with all of these rules, the bases stay the same. So back up here, let's go ahead and underline, for quotient rule, let's underline subtract the exponents. That way the gist of every rule is kind of being highlighted. So the gist of the product rule is add the exponents. The gist of the quotient rule is subtract the exponents. And then what's the gist of power rule? Multiply the exponents. All right, so we're not going to do as many examples of these, but let's do a couple. So that's supposed to be x to the fifth. I know it's kind of light. Okay, so we would keep the base the same, and we would do what with the exponents? Multiply them, so this would be x to the 20th. So even when you have something in exponential form, okay, so what would we do with these exponents just the same way that we did the first example? You would multiply them, right? So this would be 2 to the 3x times 2 power, or 2 to the 6x power. Okay? So before we move on, just know that this is not an exponential function. This is just a polynomial, okay? This is an exponential function because x is located in the exponent. Okay, so exponential functions are not x raised to a power, they're a number raised to the x power. Okay? Okay, so we're going to start to look at some equations involving exponential functions. And we're going to have to really know our exponent rules to be able to solve these. So for equations involving exponential functions, in other words, you have an exponential function and an equal sign, and you're supposed to be finding out what x is. So here is our first kind of strategy in solving these. If you can show that the bases are equal in an equation, involving exponential functions, then the exponents must be equal too. So here's the gist of this rule. If the bases are equal and you have an equation, then the exponents are equal too. Okay, so let's see if we can maybe start off small here and see if we can use this rule to our advantage. So let's say that I ask you to find x if we know that 3 to the 3x minus 4 power is the same as 3 to the 5 power. Okay, so note that the bases are the same. So if we know the bases are the same and we have two sides of the equal sign, what else do we know? We know that 3x minus 4 has to equal 5 also. And notice that's a pretty easy solving, right? So we can just add 4 to both sides. So we get 3x equals 9. And then what's the last step? Divide by 3. So what must x have been? 3. Okay. Notice that we could check this answer if we wanted to on our calculator. Just literally do 3 raised to the 3 times 3 minus 4 power. Just make sure you do parentheses around that exponent if you have one of the older calculators that doesn't open up a exponent box for you on your calculator. But what about this one? So this one might look a little more difficult. Why does it look a little more difficult? What's the base this time? E, and E, remember, is that weird number 2.718281828 forever and ever and ever. Okay. But honestly, it doesn't really matter what the bases are. We just want to note that they're what? Yeah, they're the same. So the bases are equal. So what does that mean about the exponents? They're equal also. So it's not that you're dropping the E, it's just that you don't care about it because it's already complete, if that makes sense. Like the two sides are already the same. So you're not really canceling or getting rid of it, you're just kind of ignoring it for now. And so we can solve this one too, right? So I think I'll move 3x over this way. That's going to give me 2 equals 8x minus 6. And then I think I'll move the 6 over this way, so I get 8 equals 8x. And then last but not least, divide by 8. So it looks like x is 1. Okay. So note you could check this as well, right? So I left my calculator at home too, the same place I left my pens. But what you would do is you would plug in 1 to the left side, you'd get an answer, and you'd plug in 1 to the right side, and you'd get an answer. And what would you need to verify? That they were what to each other? Equal or the same as each other. Okay. So I'm confident that you could do that, and I think maybe you should. Okay, until you kind of get the hang of it. All right, but what about when maybe we have exponents that just have a little bit more to them? So find x if we know that 4 to the 5x minus x squared power is the same as 4 to the negative 6 power. So again, make sure you're writing 4 big and then the exponent's tiny. Yes, 5x minus x squared is that first exponent. Okay, So even this squirrely problem, right? Notice that the bases are what to each other? The same. Okay. So what our rule tells us is that the exponents must be the same too. Okay, so notice this is an x squared equation, and I did that already in Unit 1, right? So what I really need to do is try to solve for x. Okay, so what do I usually want x squared equations, or really anything, honestly, if I'm trying to solve them to be equal to? 0, right? So what I'm going to do is I'm going to move x squared over to this side because I want it to be positive anyway, and then 5x as well. And again, the reason I didn't decide to move the 6 over to the left is because then I would have had a negative x squared. Okay, and I'd prefer for my x squared to be positive. It's easier to work with. So I end up getting 0 equals x squared minus 5x minus 6. Okay, so you can use AC method if you want, but I don't really think you need to. Why don't we really need to? Because the coefficient in front of x squared is just what? Just 1. Okay, when the coefficient in front of x squared is just 1, we don't really have to use AC method, but you can. But what would you get? What are the factors of negative 6 that add up to negative 5? Well, 2 and 3 wouldn't quite work, although I picked this one for a reason. Okay, so 2 and 3 won't quite work because the signs won't work out, if you think about it. Like 1 needs to be positive and 1 needs to be negative, which is going to screw up the adding to be the middle term. So yeah, we'll have to do 6 and what? 6 and 1? In other words, you can't use like negative 3 and positive 2. They won't add up to negative 5. And you can't use the other version of that either, right? Make the other one negative. So you'll have to use negative 6 and 1. So then we have x minus 6 equals 0. And what else? X plus 1 equals 0. So we end up getting two answers that would work. X equals 6. And also x equals negative 1. Okay, and again, to verify that this works, you could plug it in, but you would just have how many answers to kind of check or plug in this time? You'd have 2. Okay. Okay, so, but the question is that you might have thought already, what if the bases aren't the same? Like we've been doing problems where it just so happens that both sides have the same base. And so what we're going to try to do first is we're going to try to rewrite one or both terms so that the bases are the same. But I'm going to underline this try here because just frankly it's not always going to work. Okay, so just like when we're factoring x squared equations, it doesn't always work. This will be a nice trick, but it will only work sometimes. So we're going to have to come up with some other ways when it doesn't work. All right, so let's do a couple like that, and you're going to have to really think about your rules of exponents to kind of get these to be what we want. So let's say I wanted you to solve 2 to the 2x plus 4 power equals 16 squared. Now I always have students just want to say, oh, 2x plus 4 equals 2, and then they solve it, and then they're done in like 2 seconds, okay? So why is that, although easy, not correct? Why is it not correct to go ahead and set the exponents equal to each other right now? Yeah, the bases aren't the same, right? So we're going to need to get the bases the same, or we can't even use that rule to begin with, okay? So in other words, maybe there's a way that we could rewrite this guy so that the base would match what we have on the left. Okay, so I'm really not going to mess with the one on the left. The one on the left is already pretty much as basic as it can be. I can't break down 2 any more than it already is, right? 2 is a prime number. But I could break down 16, okay? But remember, I'm trying to break it down into a power of 2, okay? So ignore the squared power. Let's just talk about 16 for a minute. So how many 2's would I need to multiply by to get to 16? 4 of them, right? So I'm going to rewrite just the 16 as 2 to the 4th. And then don't forget about your original, the fact that it was squared. Okay, but we're almost there now, right? So now notice the left side's not changing, but now the right side I can use what rule? What rule applies when I have a power raised to a second power? The power rule, right? So we would do 2 to the 8th power using Power rule. I even said power like 4 times, right? So power rule. So now what can we do? Now we're ready to say what? Now the bases are equal, so then what can we also say? Yeah, so now 2x plus 4 is the same as 8 also. And then we're ready to solve, right? So subtract 4 from both sides, and we get 2x equals 4. And then last but not least, divide by 2. So it looks like x is 2. So you could check this on your calculator. So let me just show you how you can't use these on a test, but I can show you on my cell phone calculator maybe if it'll turn to landscape. There we go. So here's how you would kind of check it on your calculator. You'll say 2 to the power of, on this calculator I'm going to need to be a little more specific. So what would I be raising 2 to the power of for the left side? If x is 2, it's 2 times 2 plus 4, right? Which is what? To the 8th power, okay? And notice that gives me 256. Okay, so remember that one, and then let's compare that with what we get on the right side. So if I do 16 squared, then I also get what? 256, so that lets me know, hey, I did it right. As long as the left side and the right side are equal, it doesn't matter if you even get something crazier than 256. Okay, we're just verifying that we get the same thing on the left as we do on the right. Because frankly, some of those E ones especially, like you're going to get funky things on both sides. The point is, do you get the same funky thing? Okay. But Wednesday, I'll remember to bring my stuff, so.
So on the graphing calculator, is there a shortcut for E? Like, can you?
Yeah, it's on the left-hand column. So there's literally an E to the X power, and you punch that button. I think you have to use the second feature.
Okay.
Yeah.
And then it knows what number I'm putting in.
Yes, like it stores E as the 2.7 blah, blah, blah number. Yeah, definitely it knows it. Okay, so let's do one more. And then we're going to pick this back up on Wednesday. But I'll be honest, this one's kind of a doozy. Okay, so we are in no way, shape, or form ready to set the exponents equal to each other because what hasn't happened yet? The bases are nowhere near the same, right? They're not even close to the same, okay? So what we really want is for these bases to match. Okay, so which base could we use here? So remember, it's not a multiple, it's actually a power of, right? So we're going to rewrite both of these. The only one that would work is powers of 2. So let me say that again. We can't use like 4 or something because we can't write 8 as a power of 4. It's 4 times 2, but it's not 4 to a power. And the same thing here, right? The only thing that these both would break it down into base-wise would be 2. Okay, so we're just going to go one at a time, right? We're only going to focus on just the 8 part. Okay, so how could I rewrite 8 as a power of 2? Not a multiple of 2, but a power of 2. So how many 2's do I need to get to 8, in other words? 3, right? So I'm going to rewrite 8 as 2 cubed, but then I'm not going to forget that there was the x power originally. Okay, and I'll mess with that in just a minute. Okay, and the same thing here. I'm going to cover this up. I'm going to ignore this for now, and I'm going to ask myself, how many 2's do I need to get to 32, and then we'll talk about what it means, the fact that it's a fraction. So how many 2's do you need to multiply together to get to 32? It took us 4 to get to 16, so notice one more would be 5, right? So 5 would be right. So that would be 5 if it were regular 32, but the fact that it's a fraction means it's what kind of 5? It's a negative 5, right? So this is 2 to the negative 5, and then to the x minus 2 power. Okay, make really sure that you understand that we're using the power of negative 5 because it's a fraction. And then let's use power rule. It's a lot easier on the left than it is on the right. On the left, what do we get? 2 to the what? 3x. But on the left, on the left, that's what we get. On the right, we need to make sure we actually multiply or use distributive property. So notice my little arrows there, because you actually need to remember to multiply negative 5 times x, but also negative 5 times the negative 2. Okay, so I told you this one was going to be a little tougher. So this is going to be 2 to the negative 5x what? Plus 10? Okay, so that was the hard part of the problem. But now what do you notice about the bases? The bases are equal now. So what can we say about the exponents? They're the same also. And then we'll just have a little bit of solving to do, right? So we're going to add 5x to both sides. So we get 8x equals 10. And then last but not least, divide by 8. And we'll reduce that if we can. So we get 10 over 8. What goes into both 10 and 8? 2, right? So 5 over 4 is what you end up getting. Okay, so I know we would like it if we always got whole number answers, but you can get fractional answers too, okay? And frankly, this would check on your calculator just the same way. It would just be a little uglier, right? So how would you check it? You would do 8 to the 5/4 power, see what that is, and then you would do 1 over 32 raised to the 5/4 minus 2 power and see what that is and compare them and make sure they're what? The same as each other. Okay, so I know those are unusual answers, but we need to be able to deal with those as well. Okay. All right, so starting next class, we're going to jump into some scenarios where what do we do if we can't get the bases the same, which is going to be common. And then we're also going to start looking at some of our finance equations. In other words, like how much money would you have if you invested such and such amount of money at a certain amount of interest. Okay. So next time we're really going to start that business application that we really haven't been able to look at so far this semester yet.